All right, guys, in this video, this is part two of our 3-3 enthalpy practice problems and our intro to calorimetry. So in the previous video, I went through these first four practice problems, all about enthalpy change, okay? And now we're getting into the intro to calorimetry, okay? So this first question is, basically the setup is the student measured out about 50 milliliters of water, so that's going to be 50 grams of water. They put it in a styrofoam cup, and that water is about room temperature. So the water starts off with a temperature of 21.8 degrees Celsius. And then they took a piece of unknown metal and they heated it up to 99.7 degrees Celsius, and the mass of the metal was 50 grams. Okay. And then what they did is they took the metal that was at 99.7 degrees Celsius and they put it into the water that was 21.8 degrees Celsius, and they monitored the temperature. Okay. And what, if you understand what's going on, right? The metal is going to be releasing energy or losing energy or transferring heat energy to the water, and the water is going to absorb it. So the metal particles are going to start slowing down as they lose their heat, and so their temperature is going to decrease, and the water molecules are going to absorb that energy and start moving faster as they absorb the heat, and the temperature of the water is going to go up. And so what the student did was monitor the temperature, and the temperature of the water that was the highest temperature that the water reached was 24.2 degrees Celsius. So the water started at 21.8 degrees Celsius and increased to 24.2. And the metal started at 99.7 degrees Celsius and cooled down to 24.2. Now, eventually, after everything sits, everything's going to come back down to room temperature. But as the student did it, the highest temperature reached of the water was 24.2. So the metal cooled down, the water heated up until they met at that equilibrium temperature. Now, what a lot of students think that means is that the metal lost more energy than the water gained. And that's not true. Heat transfer has to be conserved. So the amount of heat lost by the metal is equal to the amount of heat gained by the water. The reason why the temperature change wasn't the same, the reason why we didn't meet right in the middle of these two temperatures is because, remember, metals tend to have low specific heat capacities compared to water. So the reason why the water didn't change as much in terms of temperature like the metal did is because the metal has a much lower specific heat capacity, or water has a much higher specific heat capacity. If they had equal heat capacities and we used equal masses, then this equilibrium temperature that was reached would be right in between. Okay. But it's not about the amount of energy being different. The amount of energy lost by the metal equals the amount of energy gained by the water. Okay. So what does that mean? It means negative Q metal. What does that mean? The heat lost by the metal is equal to Q water, which means the heat absorbed by the water. Remember, Q is heat and H is enthalpy. So if you want to change this to the letter H, enthalpy and heat are essentially the same thing at this level of chemistry. So you could say negative H metal equals positive H water. Okay. But remember what Q is equal to. Q equals MCAT, right? So what we can say is negative MCAT of the metal equals positive MCAT of the water, okay? And we have all the information, right? What's M? Mass of the metal. What's C? The heat capacity of the metal. That's what we're trying to solve for. And delta T would be the temperature change of the metal. Well, we have the initial temperature of the metal and we have the final temperature of the metal, so we can calculate the delta T of the metal, or sorry, the final temperature is this one, okay? And we have the mass of both the metal and the water. So we have the mass of the water, and they give us the specific heat capacity of water. And we can calculate the delta T of the water, right? This is the final temperature of the water. This is the initial temperature of the water. So final minus initial for the water, and final minus initial for the delta T of the metal. So all we have to plug in, so 50 grams for the metal, 50 grams for the water. C is our unknown. That's the heat capacity of the metal. We don't know. 4.184 is the heat capacity of water. The delta T of water was only 2.4 degrees Celsius, but the delta T for the metal was negative 75.5 degrees Celsius, okay? Because the metal started at 99.7 and then went down to 24.2. And so remember, you want to do final minus initial to get your delta T, okay? And so a negative times a negative makes it positive. So now everything's positive. So really we just do this, times divided by 75.5, divided by 50, and that'll get our heat capacity for the metal. And so the metal's heat capacity is 0.13, and it would have the same exact units as the heat capacity of water that we used in this equation, which was joules per gram degree Celsius. So that means for the metal, to heat up the metal by one gram of the metal by 1 degree Celsius, it requires an absorption of that much energy. Or that metal is releasing that much energy for every 1 gram of the metal that decreases in temperature by 1 degree Celsius. Okay. All right. So in the next part of this question, they tell us that the metal is gold. Okay. And we want to determine, if we take our 50 grams of metal and we want to completely melt it to the liquid state, how much energy is that going to require? And they give us some information. They tell us the melting point of gold is 1064 degrees Celsius. They're telling us our sample starting at 20 degrees Celsius, okay? And they give us the heat of fusion for gold. So remember, what heat of fusion is the energy required to melt 1 mole of a substance, in this case, for 1 mole of gold. But if you made that a negative, it would be the amount of energy released as that substance freezes. So heat of fusion is for melting and freezing, okay? But the thing to understand is you can only use this and just this if you're already at the melting point. So if we started gold at its melting point and we just wanted to know how much energy was required to melt it, we would just have to use this number and figure out how many moles of gold we have and then multiply it by this, and that'll be the energy, okay? However, we're not starting at the melting point, right? So if we kind of map out a heating curve, and I didn't draw the whole thing, we're starting down here at the solid state, right? At 20 degrees Celsius. So we have to first heat it up to the melting point. And then once we are at the melting point, we have to figure out that energy to melt it. So when temperature's changing, it's going to be a Q equals MCAT calculation. But for the phase change, that's when it's going to be a molar heat of fusion. And if we were talking about boiling, it would be molar heat of vaporization, okay? So we have to figure out this much energy, we have to figure out the amount of energy for this, and then we have to figure out the amount of energy for this. And then once we get to this point, all the gold has melted, right? So for part 1 of this calculation, it's going to be Q equals MCAT. And the reason they had to give us this melting point is because we have to use it to figure out our delta T for the Q equals MCAT. So we know the mass of our metal is 50, and in part A, we solve for the specific heat capacity, so that's where I get this from. And then the delta T, 1044, how did I get that? It was 1064 minus 20, okay? So I multiply. Now, I didn't show my units here, but remember, the heat capacity is joules per gram degree Celsius, so grams are going to cancel out and degrees Celsius are going to cancel out. So our answer to this is 6,786 joules, okay? But you might want to divide that by 1,000, so around 6.8 kilojoules, okay? And the reason that is because what are we going to do? We're going to add this energy value to this energy value, and this one's going to be in joules, and when we do this calculation, it's going to be kilojoules, and you got to either add joules plus joules, or you have to add kilojoules plus kilojoules. You can't add joules and kilojoules, right? So you don't have to, like, I don't think it didn't state in the question what energy. So you can keep this as joules, but then once you do this calculation, convert it to joules so you can add them, and you could report energy in joules, or you could report in kilojoules. It really doesn't matter. All right. All right. So in part 2, that's when we're using our molar heat of fusion, okay? And so we'll take our 50 grams, divide it by this. Remember, this is just the molar mass, so you'd have to look it up on your periodic table. Grams will cancel out. And that'll give us moles of gold, and then moles times 12.6 kilojoules. That'll give us our energy. And that comes out to be around 3.2 kilojoules of energy. Okay. So to go from here to here on a heating curve, it's going to be 3.2 kilojoules. Okay. All right. And then to get the total energy, we just add this plus this. So 6.8 plus 3.2. So it's going to take around 10 kilojoules of energy to completely melt our gold sample. Okay. All right. In the next question, another calorimetry situation. But here we're using calorimetry to figure out the delta H of this dissolving process. Okay. So we're dissolving calcium. I'll go back to the actual question. We're dissolving calcium acetate, okay, in water. And we want to know, as calcium acetate dissolves, how much energy is either released overall or how much energy is absorbed overall. Remember, when you dissolve a salt in water, it could be an endothermic process, it could be an exothermic process, okay? And we're just trying to figure out the delta H of that reaction, okay? And we wanted an energy per mole of this compound. That's eventually what we want to get. How much energy, either absorbed or released, for every 1 mole of this that dissolves, right? That's what we're trying to go to, all right? So the first thing we want to do is, look at the data. And so they took 5 grams of the salt and they added it to 50 milliliters. But remember, 50 milliliters of water is 50 grams of water. They added 5 grams of the salt to 50 milliliters of water, let all the salt dissolved, and they monitored the temperature of the solution as the salt dissolved, okay? And notice what happened. The water before the salt was added was 23.6, and the highest temperature reached as the salt dissolved was 32.3. So that tells me right away the temperature went up. And remember, we only monitored the temperature of the surroundings. The temperature increased. So as this salt dissolves, it's releasing energy. Okay? So this is an exothermic process. And so understand, if our end game is to calculate or report the delta H of solution for calcium acetate, right now I know I need to report a negative value because it's an exothermic process. How do I know? The temperature of the surroundings increased. If this number had been lower than this number, then when I'm reporting the delta H of solution, it would be a positive value. Energy was absorbed as the salt dissolved. In this case, energy was released as the salt dissolved. Okay, so that answers that first question. Is the dissolving of calcium acetate exothermic or endothermic? Well, we saw that temperature, it's supposed to be temperature increased, so it's exothermic. So the temperature of the surroundings increased as the reaction proceeds, so we know we have an exothermic reaction. The reaction released energy to the surroundings, exothermal, okay? The equation we're trying to figure out the delta H for is a salt dissolving in water. How do we write that? We write the formula for the ionic compound on this side in the solid state, and then the ions that make up 1 unit of that ionic compound on this side. So calcium acetate has 1 calcium ion and 2 acetate ions. So it's going to be, this yields 1 calcium 2 plus aqueous ion plus 2 acetate 1 minus aqueous ions. Okay, so that's the process, and that's what we're going to try to calculate the delta H of. So part C, finding the molar heat of solution with this data. Okay, so we're going to do Q equals MCAT, and they tell us to assume the heat capacity of the solution is 4.184. Okay, but this is where we got to be careful. The mass is not the mass of the solid we used, and it's not just the mass of the water we used, it's the mass of the whole solution. So we have 5 grams of salt, and it's going to become in a solution with 50 milliliters or 50 grams of water. So the mass of our solution is going to be 55 grams. So it's going to be 55 grams times the heat capacity times the delta T, that we got here, and that's going to be the amount of energy. Now remember, what this energy represents right now is the energy that was released from the reaction to the surroundings. So the reason why it's positive is this is how much energy the surroundings absorbed. Okay. And remember, it comes when you're doing Q as MCAT, it usually comes out in joules. But when we report delta H's of reaction, it's usually, we want it in kilojoules. So this comes out to be 2000 joules, which is 2 kilojoules. Okay. But understand, when we report it for the delta H of the reaction, we're going to have to change this to a negative number. So it was 2 kilojoules of energy absorbed by the surroundings, which means 2 kilojoules of energy released by the reaction. Okay. Now remember, we wanted an energy per mole of this. If we took 2 kilojoules of energy and we divided it by 5 grams of the salt, that would give us the heat of solution in energy per gram. But we wanted an energy per mole. So we have to figure out how many moles is 5 grams of the salt, and then take the amount of energy that we found here and divide by the number of moles to get energy per mole. All right. So if I take my 5 grams and divide by the molar mass, which they gave me, that tells me how many moles reacted. I take the total amount of energy produced by the reaction, divide it by the number of moles that reacted, and that gives me energy per mole. But when I report it as the heat of reaction or the heat of solution for this salt, I have to remember it was an exothermic process. So that's why it is this. Okay. So that is the answer, the final answer to part C for this calorimetry question, negative 63.3 kilojoules per mole. Okay. Again, if this delta T had been the same, let's say the same change in temperature, but it had gone down that many degrees instead of going up, then it would be this number, but I would report it as a positive value because it was an endothermic process. All right. Okay. I think, I don't, I can't tell if you see the screen anymore or not. So, I'm going to come back and I'll make a third video for this last question, number 7, on these practice problems. I had to change rooms and I think that messed up the whole recording. So you might be hearing my voice. I don't know if you can see me anymore, and I don't know if you can see the paper. So I'm just going to stop this video and make a part 3 for question 7. All right.